Chlorine atomic number is 17. So it has got 3s2, 3p5, ethyne, C2H2. That means they contain triple bond. One s orbital is mixing with 2p orbitals. Only one s orbital and 2p orbitals will undergo hybridization. Ethane, what is the formula? It is C2H6. Hello my dear students, welcome back to the session 4 on the chapter Chemical Bonding and Molecular Structure. Last class we had learnt about dipole moment in polar molecules and non-polar molecules. Also we learnt about valence bond theory, in which we learnt there are two types of bonds, that is sigma bond and pi bond. Difference between sigma bond and pi bond. Also we learned different types of overlapping to form sigma bond as well as pi bond, isn't it? So today we are going to study about hybridization. So what is hybridization? The concept of hybridization was introduced by Linus Pauling in 1931. We learnt about the overlapping of the pure orbitals which contain unpaired electrons to form sigma and pi bond. But this concept cannot be applicable for all the molecules. Thus, what he told was the orbitals, the valence orbitals containing unpaired electrons can mix with one another to give rise to hybrid orbitals. How the mixing has to occur? We shall see here. So what is hybridization? The phenomena of intermixing of pure atomic orbitals of slightly different energies and different shape to give equal number of hybrid orbitals of same energy and identical shape is called as hybridization, and the new orbital formed is called as hybrid orbital. I shall explain this now. For example, I have 2s orbital and I have 2px orbital. Okay, each contain unpaired electron, one electron each. Now s orbital has a spherical shape, p orbital has a dumbbell shape, and energy also there is difference, isn't it? But these two orbitals will mix with one another to give rise to two new orbital, okay, of same shape. Each one contains one electron each, because here also there was one electron each, and both these orbitals have same energy as well. Okay, so what is it? Intermixing of two orbitals with slightly different energy and different shape to give equal number of new orbitals of same energy and same shape is called as hybridization. So I hope you have understood what is hybridization, and these orbitals are called as hybrid orbitals. There are different types of hybridization. Also, there are some salient features of hybridization as well, which we will learn further. Now, what are the salient features of hybridization? The number of hybrid orbital is equal to the number of atomic orbital that gets hybridized. That is, how many orbitals are mixing, equal number of hybrid orbitals you will get. For example, there is 1s orbital and 2p orbitals are mixing. You have 1, 2, 3. Total 3 orbitals are mixing. You will get 3 new hybrid orbitals. Okay, so that is the meaning of the number of hybrid orbital is equal to the number of atomic orbital that gets hybridized. Second is, the hybridized orbitals are always equivalent in energy and shape. So after mixing, what hybrid orbitals you are getting, they'll have same shape and same energy, unlike the atomic orbitals which actually mixed. Okay, then the hybrid orbitals are more effective in forming stable bond than pure atomic orbitals. That is, when hybrid orbitals form the bond, that is when they overlap to form the bond, they are more effective and they are more stronger is what it means. Okay. Then these hybrid orbitals are directed in space in some preferred direction to have minimum repulsion between electron pairs and thus stable arrangement. That is, when these hybrid orbitals are formed, they will be directed in space in a particular direction, or they are placed in space in particular direction to give rise to a new geometry. So every hybridization will lead to a perfect geometry of the molecule, or I can tell that if we know the hybridization, I can tell the geometry of the molecule as well. Why? Because it is formed, the molecule becomes more stable. Why exactly? Because they'll have minimum repulsion between the electron pair. They'll have minimum repulsion between the electron pair and thus they have a stable arrangement. So I hope you will have understood this. If not, as I am explaining the hybridization, you will also learn about its geometry. Okay. Next, important conditions for hybridization. So what are the conditions for hybridization to take place? First one is the orbital present in valence shell of atom is hybridized. So which are the orbitals which are getting hybridized? The valence shell orbitals are the ones which is undergoing hybridization. Next, the orbitals undergoing hybridization should have almost equal energy. That is, they should differ only slightly with their energy. A large difference in energy, then these orbitals cannot be mixed for hybridization. Okay. Next, promotion of electron is not essential condition prior to hybridization. It is not necessary that the electron has to be promoted before hybridization. What exactly is this? You will understand it better as I am explaining further. Okay. It is not necessary that only half filled orbitals participate in hybridization. In some cases, even completely filled orbitals of the valence shell take part in hybridization. That is, not that it should contain only unpaired electron. Sometimes even if the orbital is completely filled, that is if they have 2 electrons also, they can undergo hybridization. Okay. So we will see different types of hybridization. The first one is sp hybridization. The name itself is telling which are the orbitals which is undergoing mixing. That is, one s orbital and one p orbital are the ones which is mixing to give rise to 2 new hybrid orbitals here. So what is happening is, in this type of hybridization, we have one s orbital and one p orbital which will mix with one another, or they will hybridize to give 2 new sp hybridized orbital. So you can see they have same shape, okay, and they also have same energy. Okay, so 2 are mixing, I got 2 new hybrid orbitals here. Hybrid orbitals always is shown one with the bigger lobe and one with the smaller lobe, and for our convenience the smaller lobe can be skipped when we are drawing the full structure. So how are they directed in space? That is, I have my first orbital, that is sp hybridized orbital. This is my second sp hybridized orbital. They are placed opposite, or the angle between these two is 180 degree. So they give rise to linear structure. Okay. So sp hybridized orbital shown together only with large lobes. Okay. Now in sp hybridized orbitals, 50% of the orbital will have s character and the 50% has p character, because we have one s orbital and one p orbital which is mixing. Okay. The 2 sp hybrid orbitals are oriented in opposite direction, forming an angle of 180 degree. Okay. Now we'll see the example for sp hybridization, that is BeCl2, beryllium chloride. Okay. So in beryllium, in ground state is the normal state before it forms the molecule. Okay. So ground state, the electronic configuration is 1s2, 2s2 because atomic number is 4. Now in s orbital, I have 2 electrons and 2p orbital is empty. Okay. Now before it forms the molecule, what happens here is the electron in the s orbital will jump to the empty p orbital. So you will get 1 electron in 2s and 1 electron in 2px. Okay. So that state is called as the excited state. Just before it forms the molecule or just before it undergoes hybridization, what happens? There is promotion of the electron from 2s to 2p. Now these two orbitals, one s orbital and one p orbital, will undergo sp hybridization. That is, one s orbital, one p orbital will undergo sp hybridization to give 2sp hybridized orbital, which is oriented opposite to one another and giving an angle of 180 degree. So beryllium has got, this is first sp hybridized orbital, this is another sp hybridized orbital with 1 electron each. They both had 1 electron each. Okay. Then what happened? Chlorine atomic number is 17. So it has got 3s2, 3p5 electrons in the valence shell. So if I draw this orbital diagram, so 3s2 electrons are there and 3p, 1, 2, 3, 4, 5. 5 electrons are there in 3p. So we have one p orbital which contains only 1 electron. So chlorine I can represent like this. This is the p orbital with 1 electron. Like this, I have 2 chlorine atoms. I have 2 chlorine atoms like this with 1 electron, p orbital. So beryllium has got 2 sp hybridized orbital with 1 electron each. Chlorine, p orbital with 1 electron each, will overlap to form sigma spp bond. That is, sp hybridized orbital is overlapping with the p orbital of chlorine. So one sigma bond is formed here. Similarly, one more chlorine atom, p orbital, will overlap with sp hybridized orbital of beryllium to form another sigma bond. So the molecule will be beryllium, chlorine and the bond angle is 180 degree. So I hope you have understood sp hybridization in beryllium chloride. Okay. Next we have one more example of C2H2, that is acetylene. Very important. Okay. Or I can also call it as ethyne. C2H2. That means they contain triple bond, isn't it? Ethyne, that is 2 carbon atoms with 3 bonds and 1 hydrogen and 1 hydrogen. This is the structure if I have to write. Now what happens with the carbon atom, we'll see. Electronic configuration of carbon atom is 1s2, 2s2, 2p2. Correct? In ground state, what happens? There is 2 electrons in s orbital and 2 electrons in p orbital, which I have written 1 each in 2px and 2py. Now, before it forms the molecule, here the electron from 2s will get promoted to the empty 2pz orbital. So now 2s, 2p, 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 2px, 2py, 2pz. Each have 1 electron each, that is unpaired electron is there. Now when the carbon atom is forming ethyne molecule, what will happen? 1s orbital will mix with 1p orbital. What is it? 1s orbital will mix with 1p orbital to undergo sp hybridization, and the 2 orbitals, pure orbitals form pi bond. Okay, so they remain unhybridized. They will just remain as it is with one electron each. So now I have shown two carbon atoms because I have two carbon atoms here. Okay, so my first carbon atom, I have one sp hybridized orbital. This is my second sp hybridized orbital. This is my second carbon atom with one sp hybridized orbital, my second sp hybridized orbital. You can see that two sp hybridized orbital with one electron each have overlapped with one another to form one sigma bond. Correct? Then we have one more sp hybridized orbital of this carbon remaining, which is overlapping with hydrogen to form another sigma bond. Similarly, here we have for the second carbon atom one sp hybridized orbital which is overlapped with hydrogen atom to form the third sigma bond. So in this structure I have 1, 2 and here 3. 3 sigma bonds are formed. Now we have the p orbitals of both the carbon atom which is unhybridized. I told you there are two p orbital which is unhybridized, which is shown in green here. Okay, so we have, this is my first unhybridized p orbital, this is my second unhybridized p orbital. Similarly, we have one unhybridized p orbital, the second unhybridized p orbital which contains one electron each. Now they will bend sideways to form pi bond. So these two will overlap with one another, okay, on both the ends, from below as well as from above. Similarly, you have the other two also which will overlap with one another to form pi bond. So two pi bonds and one sigma bond is there between the two carbon atoms. So you can see the angle is 180 degree itself because sp hybridization, they are linear. They are placed opposite to one another, the hybridized orbital. So we will get a linear structure with 180 degree angle. But between carbon and hydrogen it's a sigma bond. Carbon and hydrogen it's a sigma bond. One of the bonds between carbon and carbon is sigma bond. The other two are pi bonds. Okay. So I hope you have understood about the sp hybridization. One in beryllium chloride, another one in ethyne or acetylene. Okay. Next we have is sp2 hybridization. Again the name itself tells one s orbital is mixing with two p orbitals. Okay. So we have one s orbital and two p orbitals which is mixing with one another or getting hybridized to form three new hybrid orbitals. Three new hybrid orbitals which is having an 120 degree angle between them. Okay, so they are having how much angle? 120 degree angle, and they are planar also. Okay, thus the three hybrid orbitals are oriented in trigonal planar symmetry with bond angle of 120 degree, and the sp2 hybridized orbitals have 33.3% S character and 66.6% P character. Okay, we'll see the example of sp2 hybridization. First one which we have is BCl3, boron trichloride. Okay, so electronic configuration of chlorine 1s2, 2s2, 2p6, 3s2, 3p5. So in p orbital I have 1, 2, 3, 4, 5. One p orbital which is having unpaired electron. Okay, coming to the central atom, that is boron. Electronic configuration of boron in ground state is 1s2, 2s2, 2p1. So in excited state what is happening? This one electron is getting excited to go to empty 2py orbital. So you have one electron in S, one electron in 2px, one electron in 2py. Okay, now 1s orbital, 2p orbitals undergo sp2 hybridization. Okay, how many hybrid orbitals I'll get? 3 new hybrid orbitals I'll get. And for boron, this is my first hybrid orbital, second hybrid orbital, third hybrid orbital. Okay, so each one contains 1 electron each. So if it is boron, I have first, second, third, 3 hybrid orbitals with 1 electron each. See, 1 electron each. Now they will overlap with chlorine atoms, p orbital. Okay, with 1 more electron to form first sigma bond, second sigma bond, and the third sigma bond. And the bond angle is 120 degree. So I hope you have understood about the hybridization. I have 1 s orbital, 2 p orbital to give sp2 hybridized orbital with 1 electron each here. They will overlap with chlorine atom to form sigma bonds. Okay. Next we have formation of ethene molecule, that is C2H4. Okay. Here it is the same way, carbon atom in ground state as well as excited state have same electronic configuration just like ethyne. Okay. So electronic configuration of carbon is 1s2, 2s2, 2p2. 1 electron from the s orbital is going to the p orbital to get 1 electron in 2s, 1 electron in 2px, 1 electron in 2py and 1 electron in 2pz. But when ethene molecule is formed, only 1 s orbital and 2 p orbitals will undergo hybridization, that is sp2 hybridization will take place, and 1 p orbital will remain unhybridized, or it will remain as it is, pure orbital. Okay. So what will happen when they mix? First carbon atom I will get 1, 2, 3. I got 3 sp2 hybridized orbital with 1 electron each. Similarly, I take one more carbon atom. I've got 1, 2, 3 sp2 hybridized orbital with 1 electron each. Now these two will overlap with one another. See, here you can see one sp2 orbital and the other sp2 orbital will overlap with one another and get 2 electrons to form one sigma bond. See, here I have shown the sigma bond. Then you have one more sp2 hybridized orbital will overlap with hydrogen, that is these two will overlap with one another. Then we have this will overlap with hydrogen to form second sigma bond. This will overlap with one more hydrogen to form another sigma bond. So you have hydrogen and hydrogen, okay, to form 2 more sigma bonds. Similarly, here also you have hydrogen with 2 electrons you will get. Here also it will overlap with hydrogen and 2 electrons to form 2 sigma bond. So here also hydrogen, hydrogen overlapping to form which bond? Sigma bond. Then where is the pi bond? We have in ethene we have a double bond, isn't it? So we have this unhybridized p orbital which is left. Here you have, this is the unhybridized p orbital which we have, and they also contain 1 electron each. Now this one will overlap sideways. You can see here they will overlap sideways to form 1 pi bond. So in ethene you have 2 carbon atoms, 1 bond, sigma bond, that is formed by sp2 hybridized orbital overlapping with one another. Then you have the p orbital overlapping sideways to form pi bond, and then you have hydrogen overlapping to form sigma bond, another hydrogen sigma bond, another hydrogen you have sigma bond, and the other hydrogen you have a sigma bond. So this is the structure of ethene molecule, and the bond angle is what? 120 degree. I hope you have understood about ethene molecule. Okay. Next what we have? It is sp3 hybridization. Again the name itself tells sp3 hybridization means 1 s orbital and 3 p orbitals are undergoing hybridization. So 4 sp3 hybrid orbitals are formed, new orbitals. You can see we have 1 s orbital, 3 p orbital which will intermix, undergo hybridization to form 4 new sp3 hybridized orbital which is put together the bond angle will be 109.5 degree. It has got a tetrahedral structure. 109.5 degree angle between the sp3 hybridized orbitals. Okay, so it is a tetrahedral symmetry with 109.5 degree angle. There is 25% S character and 75% P character in each sp3 hybridized orbital. So we'll see the example now. Next, we have example of methane molecule for sp3 hybridization. So methane is having a formula of CH4. So we have carbon atom electronic configuration as 1s2, 2s2 and 2p2, isn't it? I have 2s2 and 2p, I have 2 electrons. So one will move to the empty orbital to give the electronic configuration of 2px1, 2py1 and 2pz1. Okay. So we have 2s1, 2p, 3 electronic configuration. Now all of this will mix, all the 4 orbitals will mix to give rise to 4 new hybridized orbitals. Okay. Now each one of the hybridized orbital will overlap with 4 different hydrogen atoms to give a sigma bond. So you have a sigma bond here, sigma, sigma and sigma bond, and the bond angle is 109 degree 28 minutes or 109.5 degree. Okay. So I hope you have understood about sp3 hybridization in methane. Okay. One more we have is about ethane molecule. Ethane, what is the formula? It is C2H6. Okay. So we have 2 carbon atoms again. So the electronic configuration of carbon is 1s2, 2s2, 2p2. So 1 electron from S has got excited and it has gone to 2pz orbital. 1 electron each in 2s orbital and 2p orbitals. So all of this will undergo hybridization. So you have the first carbon atom, second carbon atom. Here it has got hybridization 1, 2, 3 and 4. Similarly here you have got 1, 2, 3 and 4. Each have one unpaired electron. Okay. Now first the 2 sp3 hybridized orbital will overlap with one another to form sigma bond. Okay. Then what do we have? We have 3 hybridized orbital on this carbon atom, 3 on the other carbon atom. Each will overlap with hydrogen. Each will overlap with hydrogen to form sigma bonds. Okay. So here you can see each one has overlapped with hydrogen to form sigma bonds. How many sp3 sigma bonds is formed? sp3 with s orbital, 6 are formed. 1, 2, 3, 1, 2, 3. Okay. So this is the structure of ethane molecule. What is the angle? It is 109.5 or 109 degree 28 minutes. Okay. Next class we'll be learning about valence shell electron pair repulsion theory and shapes of molecules containing bond pair and lone pair. So I hope you have understood today's class. It's very important to understand and learn different types of hybridization and example for each type of hybridization. See you next class. Stay tuned, stay curious, stay focused.